We're going to start a series of videos on polynomial functions. So let's dive into some of the things that we already know based off of different key features. Here we have a polynomial that's graphed for us, and we want to describe the domain of the function. If I'm looking for any breaks in the domain going left to right, we see that every x value has a defined output. So the domain of this function would be negative infinity to positive infinity, or all real numbers. If we think about the range of this function, it's going to keep going down to negative infinity, so we're going to start there at the negatives. And we're looking to see, are there any breaks in the range of this function? And this one doesn't have any. We're going to hit every y value from negative infinity to positive infinity as well. The y-intercept of this function, where it crosses the y-axis, is a little bit before -1, and we just have to estimate. So I'm going to estimate that to be roughly around -0.9. Sounds like a good estimate. The x-intercepts, where it crosses the x-axis, I can see clearly happens at -4, -2, 1, and again at +5. So there are multiple x-intercepts. So I'm just going to list them out as coordinates. So -4, 0. We have another one at -2, 0, 1, 0, and then lastly again at 5, 0. Relative maximums and minimums are different than absolute maximums or minimums. These are also called local max and mins. So this is happening at those peaks or valleys that we see. So any peak would be a relative maximum. So there's one roughly here a little bit after -3. So I'm going to estimate that's -3.2 maybe, and then go all the way up, and it's almost at +3, so maybe 2.9. There is another mountain or peak that happens here at the x-intercept 1, 0. That is still a relative maximum, so 1, 0 is a maximum. The relative minimums are those valleys. I have one here that's roughly kind of around -1, so I can estimate maybe -1, -1.5. If you're arguing that like that's a little bit before -1, like -0.9, that's fine too. It's really subjective because we don't have an exact point right there for me to locate. All right, this one down here, it's maybe right before 4, but I'm just going to estimate +4, then -8 point something. So I'll say +4, -8.7. End behavior is something we haven't necessarily talked about, but if we read what's happening, it says as x goes to, that's what the arrow means, as x goes to positive infinity, the function f of x is approaching some other value. So if I read my x-axis, as we go to the right to positive infinity, our function is just going to keep going up and up and up and up. So it's going to be approaching positive infinity. As x goes to the left at negative infinity, we're going this direction. If I read backwards to the left, our function is going to keep going down to negative infinity. So end behavior is a new concept for us, but that's describing what value or possibly values the function's approaching at the ends of the function. It doesn't really matter what's going on in the middle, we just care about the end of the function. And we're going to look to see what happens as x approaches positive infinity to the right side and as x approaches negative infinity, which is the left side. We write it using this notation that we kind of explained with the arrows as x approaches or goes to positive infinity, f of x or y approaches some other value. Now, a polynomial function could be any function in the form where it says y equals a x to the n power plus b x to the n minus 1 power plus c x to the n minus 2, and so on. In its standard form like this, we can see the highest exponent, x to the n power, and that is the degree of the polynomial. That greatest exponent is typically the first term. Like when we were talking about quadratics, we usually write ax squared first, but we do need to check to see first that it's in standard form, because if it's in factored form, then we would need to expand it all the way out to see what standard form looks like. In a quadratic that we have seen, that would be a degree 2 because the highest exponent is 2. But a cubic polynomial would be degree 3, a quartic polynomial is degree 4, and so on. We can also talk about a non-zero constant, something like y equals 5 or f of x equals 5, where it doesn't really even have an x variable. In that, x is to the 0 power, so we would say that's degree 0. Now this section we're supposed to use Desmos for, but you can just kind of graph these on a calculator or Desmos, any kind of tool, and look to see what's happening with these functions. I'm just going to sketch these out for us, but we have y equals 2x squared, which is just a parabola that's been stretched by a factor of 2, so it's like a little skinny parabola. If I have 0.4, not 0.5, x to the 4th, this is going to be another parabola-ish shape. It might look a little steeper. If I did 0.5 x to the 4th, that 0.5 is a vertical shrink. So it's going to maybe make this a little skinnier, not skinnier, a little flatter. And 1/10 x to the 6th. Now we haven't probably seen an x to the 6th power one, but this would be a little bit more flat since it's 1/6, and it would look something a little bit like that. What we'll notice is that all of these polynomials have a up behavior where they're pointing up on the left and up on the right. So if we describe what we see, we can call that up, where it's going up on the left, up on the right, no matter what. The formal notation would say as x approaches negative infinity, which is to the left, y or f of x approaches positive infinity, since that's going up to positive, and as x goes to positive infinity, which is the right side, y is approaching positive infinity as well. The next one has cubic functions and some other odd degree functions. We've seen a cubic function before. It looks something similar to this. 1/4 x to the 5th. Makes it look a little bit flatter, but it does look something like that. Even if I did 0.001, that 0.001 is a vertical shrink. And maybe I get something that looks like this. 1/10 x to the 5th, maybe it's not as shrunk, but still probably looks something like that. What we'll notice is that it's going down on the left side and up on the right side. So we often would classify this as down-up behavior. Formally, we can write it out as x goes to negative infinity, which is the left side. Our function's going down to negative infinity, so y approaches negative infinity. And as x goes to positive infinity, your y value is approaching positive infinity because it's going up. If we summarize some of these in behaviors, we can have an even degree with a positive coefficient, something like a quadratic. This is going up on the left, up on the right. Once we make that a negative coefficient, think about, here's an example of just y equals x squared. That was a positive coefficient. But if I do a negative that reflects it over the x-axis. So now this is going to flip it down, and we would have a down-down behavior. An odd degree with a positive coefficient was something like x cubed. We know what that graph looks like. It's one of our parent functions where we're going kind of curving around, but we go down on the left and up on the right. If we reflect it, if we do negative x cubed, it is reflecting this cubic polynomial. So now it's going to go up on the left and down on the right. Those key features about the end behavior will help me describe and even graph some polynomials. But we can look at the polynomial equation and see what it's going to be just from the standard form. So here I have negative 1/10 x to the third plus 5x squared minus 3x plus 2. The leading term is negative 1/10 x to the third. So it has a negative coefficient. And it's degree 3. That means we have an odd degree with a negative coefficient. So it has been reflected. I don't know exactly what's going on in the middle, but I know that it's going to go up on the left and down on the right. So it has that up-down behavior. Now we could formally write that out as x goes to negative infinity, which is the left side. Y is going to go to positive infinity. And as x goes to positive infinity, the right side, y is going down to negative infinity. Looking at b, our function is not in standard form. We have something in factored form. Even though it's in factored form, we can still figure out what this would look like, what the degree might be. And one way to do that is to think about these powers. If we were to expand out this x minus 2 squared, we would end up with an x squared as its highest power. We already have this x to the third, and multiplying that by x squared makes that x to the fifth. Multiplying that by another x to the first power makes that x to the sixth. So this is going to be a degree 6 polynomial. But maybe you need a little bit more of that, so I'm going to actually multiply this out and show how would I convert that all the way to standard form. Now we know x minus 2 squared means there's x minus 2 times x minus 2. So let's even distribute that part. Maybe you already know what that squared looks like. But that ends up being x squared minus 2x and minus another 2x and minus 4x plus 4. And we're multiplying by x plus 1. I'm going to leave that negative 5x cubed out and just distribute this section. If I distribute x squared times x, that's x cubed. X squared times 1 is 1x squared. Then we distribute our negative 4x. So negative 4x times x is negative 4x squared. Negative 4x times 1 is negative 4x. Distribute our 4. Plus 4x plus 4. And we can combine like terms. We've got negative 5x cubed still hanging out here, multiplied by x squared minus 3x squared. I'm sorry, x cubed minus 3x squared. But the negative 4x and positive 4x just add to 0. So I'm going to leave out that because there's no point in writing 0x. But then we have this positive 4, and I can distribute again. We've got negative 5x to the 6th power plus 15x to the 5th power minus 20x to the 3rd power. But what we'll notice is that it was a degree 6 polynomial. So the other thing we would want to look for is that leading coefficient. we really don't care what the actual value is, but we do care about what the size, if it's negative or positive. And so in this one, negative 5x cubed times a positive x squared times a positive x is going to be a negative coefficient. In this case, it's an even degree and a negative coefficient. With that, think about your quadratics, even degrees that have been reflected over. So this makes a down on the left, down on the right behavior. Maybe it's doing something funky in the middle. We don't really care about the middle. The end behavior is down, down. Now formally, this would say as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to negative infinity. The next video, we'll start right back up with this standard form.